Hello again and welcome to another chemistry lesson. I'm still summarizing our organic chemistry, and we're looking at the properties of organic compounds. Now, if we're talking about the properties of organic compounds, we are basically talking about the following three properties. The first one is the boiling point. Okay, the boiling point. Now, you will recall that the boiling point refers to the point at which, or the temperature at which something goes from a liquid to a gas. Okay, from liquid to gas, and then related to the boiling point is also the melting point. Melting point. So, if something has a higher boiling point than something else, then it will also have a higher melting point than something else, and we'll explain now why. Melting point would be going from a solid to a liquid. Okay, and then that's the first one we're going to look at. The next one we looked at was the vapor pressure. The vapor pressure. Now, vapor pressure had to do with where there is not heat added. In other words, we're not increasing the temperature, and yet we are still going from a liquid to a gas, but this time we go from a liquid to a gas because on the surface of the liquid there are some particles that have enough energy to escape. Okay, so in other words, the forces that exist to keep the molecules as a liquid are not enough to let the surface molecules stay intact with the rest of them. Okay, so that causes a vapor. Okay, and the higher the vapor pressure, the more of these molecules are escaping, causing pressure. If we were to put this in an isolated system, that would cause pressure. That was vapor pressure. Okay, then we also look at the viscosity. Viscosity, I think it's spelled like that. I always forget. Anyway, viscosity is resistance to flow. Resistance to flow. Okay, so something like syrup has a very high viscosity because it flows very slowly. Well, something like alcohol, on the other hand, has a very low viscosity because it flows very easily. Okay, so these are the main elements that we are going to look at, but all of them rely on the same thing. They rely on intermolecular forces. Intermolecular forces, and we looked at these forces. Intermolecular forces refer to the forces that exist between molecules. The forces that exist between molecules in which they are attracting one another. Now, the type of forces that exist, or that we get, the first one we looked at is dipole-dipole. Dipole just means two poles. Okay, that's what the di means. Poles means these two poles, a positive and a negative pole. Now, dipole-dipole forces are talking about forces where the one element has the one atom in a molecule is positive, the other atom in the molecule is negative, and so in other words, it's ionic bonds, primarily ionic bonds, or at least polar bonds. Ionic and polar molecules usually have this. That is where the positive side of the one molecule and the negative side of the same molecule attracts the opposite, the negative of another molecule with a positive of the molecule. Okay, and that causes the attractive force, and it's a very strong, it's the strongest force between molecules. Okay, that's dipole-dipole. The other one we look at is in dipole-induced. Actually, before I get to dipole-induced, let me first do the hydrogen bonds. Okay, hydrogen bond, even though it's hydrogen bond, it's not technically a bond. It refers to the force that exists when hydrogen plus a high electronegative covalent bond. Okay, so that's like OH, the OH ion, or water. Okay, oxygen has a high electronegativity bonded to hydrogen, which is lower respectively to that, which gives the oxygen quite a high attractive force for the electrons. So it draws the more electrons to itself, making this molecule negative towards the oxygen and positive towards the hydrogen, which again causes this dipole that we saw in dipole-dipole forces. And just so you know, the dipole-dipole forces, if it's ionic, if it's two ionic bonds, it's ion dipole. Okay, but both of them ion dipole. Both of them are very strong forces, but ion dipole would be the strongest one. Hydrogen bond is the next one, and it's also very strong forces that attract molecules between each other. And then after hydrogen bonds, other examples can be hydrogen with any of the group 7 elements. That would also be hydrogen bonds, but let's leave it there. Then we move on to the next one, which is the dipole induced. Okay. Dipole induced is slightly different than what we've seen thus far. In a dipole induced happens more when it comes to a molecule, especially the bigger the molecule, because dipole induced refers to when that molecule has a negative charge somewhere on that molecule, not because the atom itself has a negative charge, but the grouping of electrons at a certain moment is just high. Okay, so just at any given moment there might be an extra or a thicker grouping of electrons at one time, giving the molecule at that moment a negative charge. Now, the larger that molecule is, the more surface area there is, the more likely there will be for electrons to group together like that, just momentarily, and that is why it's called dipole induced. It's not a permanent dipole, it's a temporary dipole that changes with time. But again, the bigger the molecule, the more likely it is that this happens. Okay, so the bigger the molecule, the stronger the dipole induced forces will be. Now, these two together are called van der Waal forces. Okay, this dipole, in other words, in covalent bonds excluding hydrogen, but in the dipole are covalent bonds, and dipole induced are also covalent bonds, and in them we find van der Waal forces, and this specifically, this one is called London forces, and these are very weak forces. London forces are very weak forces which increase with an increase in the surface area or the size of the molecule. So let's then use what we've learned so far to actually allocate which type of forces occur in different functional groups. So in our alkenes, we had carbon, single bonded to carbon, single bonded to carbon, and here we can see that in this case there is hydrogen and carbon don't have a big difference in their electronegativity, so it's not a hydrogen bond. Carbon doesn't have a high electronegativity, so it's not a hydrogen bond. It's not an ionic bond either, otherwise it would have been an ion dipole forces. So what we do have here are these dipole induced forces. So in this case we have weak London forces. Weak London forces. forces in here. Okay, now the moment we have a double bond, okay, it's still the weak London forces in the alkenes. So this is the alkanes. Okay, and the alkenes also have weak London forces, although the likelihood of a grouping of electrons is slightly higher at this double bond, because remember, I'm sharing electrons, where here my electrons are slightly more scattered. Here I'm sharing electrons, so there's a good likelihood that at that point I might just have a negative charge, slightly negative charge, and therefore attract the rest of them, another molecule, alkene molecule, that has a positive charge. So this one, these forces are slightly higher than the alkenes. Okay, so the alkynes exactly the same. It will have the strongest among the three weak London forces. So it's still weak London forces. Let me short it to that. Weak London forces, but again, there's a very high likelihood that at this point we have negative charges. Now, in all of these, obviously, what you should notice is that with a bigger an increase in the number of carbons, if we increase the number of carbons, so if the number of carbons increase, this will increase, or the chain length, this will increase the size of the molecule, or the surface area of the molecule, giving us a higher likelihood to have a grouping of negative electrons. Okay, so all of these depend on the size of the carbon. Now, and I didn't mention it a little while ago, but I'm sure you get it now. These intermolecular forces have a direct influence on the boiling point. The stronger the forces, the higher the boiling point, because the more difficult it is to get the molecules to separate from being a liquid to becoming a gas. Vapor pressure, exactly the same. The higher the intermolecular forces, sorry about that, the higher the intermolecular forces, the stronger forces exist keeping it as a liquid. Okay, so which means less of the vapor escapes. So let me do it like this. When IMF increases, so if IMF were to increase, the boiling point, stick to the color, the boiling point will increase. If intermolecular forces increases, then the vapor pressure will decrease, because less vapor will form, because the forces are stronger. Viscosity, the stronger the forces are, the more the molecules want to stay together, so the more they resist change in their shape. That's what viscosity can also be, is changing its shape. So it increases when the intermolecular forces increase. In other words, when we are increasing a carbon chain, the length of a carbon chain, we are increasing boiling point, decreasing vapor pressure, increasing viscosity. I hope that makes sense. Okay, so we move on to the next type. These were the I've got some space here. The next type we looked at were the haloalkanes. Okay, haloalkanes. Okay, now with the haloalkanes, we had a carbon bonded to a halogen. Now, in this case, this is a dipole itself. Okay, why is this a dipole? Remember this, what we mean by a dipole is that when these two atoms bond with one another, one is drawing electrons to himself, making him positive. So why is this a dipole covalent bond? Because the electron, or the halogen, the halogens, you have to remember, halogens on the periodic table have the highest electron negativities in their row, so they have a very high desire for the electrons, drawing electrons to themselves. and therefore they are highly electronegative, and then interacting with other elements on the periodic table, they will therefore create dipoles, at least dipoles, even ionic dipoles. Okay, so this one would be dipole. Dipole is a stronger force. Okay, so for example, if we were to have methane and chloromethane, okay, which one will have the higher boiling point? Okay, it will be, or actually let's do it at least with two so that we can see. Okay, so if I had ethane or I have chloroethane, which one will have the higher boiling point? Well, chloroethane is more likely to have a negative charge on the side of the chlorine, which means it is more likely to attract other other molecules on the negative side. Okay, so these aren't bonds. Okay, just don't see them as bonds. Okay, so it's more likely to attract the positive side of another molecule, and therefore the forces that exist between the molecules are higher. What that means is that it will have a higher boiling point, a lower vapor pressure, and a higher viscosity than an alkane with the same number of carbons. But again, the same thing applies. If I increase this carbon chain, this longer chain will have stronger forces, even in chlorine. That will be the case in all of these compounds. The longer the chain, the stronger the forces. Okay, so that was the haloalkanes. Then we also had a look at alcohols. So where am I? Okay, we had a look at the alcohols. Now, what type of forces exist in the alcohols? In the alcohols, we have carbon bonded to a hydroxy. Now this, you can see, that's why I mentioned this. This was where the hydrogen bond came into play, and the hydrogen bond definitely causes definitely stronger forces even than dipole-induced forces at sometimes. Okay, so alcohols have also have hydrogen, not hydrogen forces, but hydrogen bonds. It is slightly a wrong word, but that's the forces that exist between the molecules. So in other words, this one will have a negative, especially at the oxygen, will have a negative charge on there, and therefore attracting more positive ends of other molecules. Okay, that's the alcohols. Again, so that's the type of force that exists in it. Again, same thing applies. As I increase the carbon chain, I increase the strength of the forces. That's alcohols. And then when we look at the carboxylic acids, you remember carboxylic acid has a general structure like that, and lo and behold, we have a hydrogen bond forces in here as well. So these two will have the same type of forces acting in them. And then lastly, we have the other carboxyl the other carboxyls. In other words, they are carbon double bonded to other things, and you remember we have the esters, the aldehydes, and the ketones. They all have different, but I'm just going to stick to the carboxyls here. The carboxyl derivatives, they will all have dipole forces. They will all have dipole forces, and the reason why they have dipole forces is because this is a dipole. Again, the difference between the electron negativities for carbon and oxygen is high. Okay, which well, not as big, but it's large enough to cause that the one with the higher electron negativity, that's oxygen, will attract the electrons more to itself. And even since there's a double bond there as well, there's a very high likelihood of there being a congregation of electrons in this area. Okay, and that means these are also strong forces that exist here, and again all of the rest applies. So if we know what type of force works in a certain element, we can decide, compared to another element with a similar number of carbons but a different force, we might know how they relate to one another. The last thing I just want to mention is, what effect does branching have? What do branches do? And I'm sorry, this is really messed up, the way I'm writing all over this page. Okay, but what does branching do? Okay, well, you can imagine if I have a bunch of branches here. This is now normal tree branches. Okay, if I were to take 2 branches from a tree, and each of those branches have branches themselves, then it would actually be difficult to bring these 2 close together. And the closer they were together, if they had any forces attracting one another, then they would be able to come the closer they are, the stronger those forces would be able to have an effect. But when they have branches, then coming close together is quite difficult. That's the exact same thing. When the number of branches increase, when the number of branches increase, the intermolecular force that the effect of the intermolecular force is lower. Okay, so more branches mean I can have 2 elements with the same number of carbons, but the one has his carbons nice in a straight line, and the other one has his carbons with one branch, for example. And this one will, his intermolecular forces will have a weaker effect than this one's intermolecular forces, because the branch is making it difficult for the for different molecules to actually come close enough and be attracted. So I hope that makes sense. That's as much as I want to say. This video has been dragging on long enough, but basically, if I summarize it, we have dipole-induced forces in our hydrocarbons. We've got dipole forces in our haloalkanes, our alcohols, and our our alcohols, and I didn't write it here, carboxylic acid and alcohol, they have hydrogen bonds because of the hydroxy ion, and then carboxyl derivatives all have dipole-dipole forces. So thank you very much for watching. I hope you learned something, and that this was a good enough summary for you. We'll see you in the next video. We'll try and summarize the different reactions that we encountered in organic chemistry. See you there.